about my dual citizenship. Or acknowledgement. I just
Yeah, my mom's, is it? Yeah. Boyfriend. Going down there, I'm gonna eat shit. Oh, and then I also find I like.
Okay,
Yeah.
thank you very much for all your ideas.
Under what?
Our two things, heard lots and lots of practice types of ideas. So I'll go through, summarize those and start to figure out how we can nest those things into how we work together. So hopefully that means next week will look a little different. We are just gonna finish out that membrane transport 3 packet today. That'll give us time to reset so that we're all fresh and ready to think about neurons and nerves and how they work. Sorry. Say some of our yeah, I won't say anything about that. Okay. All right, so when we left off, our last topic before the exam was osmosis. So we talked about how that's the movement of water, how water moves essentially towards high concentrations of solutes. We saw that we measured that with something called osmolarity, right? And we have a related concept called the osmotic pressure. So both of these are telling you where's there a pull on water, essentially. That was nested into our previous. One thing that I do want to, or our next little section here is the difference between osmolarity and tonicity. So you might have used the word like isotonic before when you were talking about osmosis. It's a similar concept to tonicity, but it's slightly different. Okay. So it works almost exactly the same way, but when you talk about tonicity, you're specifying that the solutes you're talking about are something that can't cross the membrane. Okay. So this is helpful because if your solute is something that could cross the membrane, well, then it's going to start moving, right? Which has an impact for how much water moves. But when you're talking about tonicity, you're specifying, you're talking about impermeant solutes, so things that can't cross the membrane, which means it absolutely has to be only the water doing the movement. Right? So that's why in earlier coursework they usually use isotonic, hypertonic, hypotonic, because they embed in that word that we're talking about impermeant solutes. Okay. So to just see why that makes a difference, you can think about a situation that starts out isoosmotic, but not isotonic. So in this situation, we have an isoosmotic solution because if we do the math, we find that we have the same osmolarity inside and outside the cell. So we have 300 million osmoles inside and outside the cell based on all those solutes dissolved in. So isoosmotic, same as iso, but they're not isotonic because tonicity has to do with, are we thinking about things that can cross that membrane or not? So what we're saying is that while there's the same amount of general stuff on either side of the membrane, we don't have the same amount of impermeant solutes on each side. We don't have the same amount of stuff that is stuck. Okay. So as we see time progressing, right, we can see here the inside of the cell originally contains all our impermeant solutes. So the stuff that can't move here is inside the cell. And outside the cell, we have urea, which can actually cross the membrane. So what starts to happen, we do have water flowing into the cell for the reason of that urea starts to spread out. So it wants to reach equilibrium with itself. So some of that urea, which is highly concentrated outside the cell, moves into the cell. And you can think, we're not going to do the math, but you can think how this would raise that 300 number, right? Because now we suddenly have more yellow, more dots overall inside the cell. We have both that impermeant solute in purple plus some of the urea in yellow. The purple dots can't get outside the cell, so it's only those yellow dots moving, only the urea. So this ends up with a situation where you have more than 300 milliosmoles inside the cell when we measure their osmolarity at a second time point. So that's why we would see water starting to flow, even though we started out with a situation that started out as isoosmotic. Now we'll tell you about the osmolarity and tonicity stuff. We don't need that for our next unit. We don't need that for neurons and synapses and understanding the brain. When you are going to need this is in A&P 2, when we come back to talk about kidneys and the renal system. So this comes back eventually, but this is not an immediate priority for us. Those are just some definitions. I don't expect you to memorize these concentrations right now, but you can see here that osmolarity is permeant and impermeant things. Tonicity has to do with the impermeant things. A fun little trick is that the cell volume, we saw that when water moves into or out of cells, we can kind of do that in terms of fractions or doubling in size just by looking at the osmolarity. So you can see here, we start with a cell volume of V0, O is for original, I guess. So their original volume. And we start with a situation where the osmolarity inside the cell is twice what it is outside the cell. Okay. So we're in a hypotonic solution. Okay. So we're going to have water move in to water down that 300 milliosmoles. So it was twice what the outside was when it comes to equilibrium. So it becomes isoosmotic due to water flowing in. That cell volume is now twice the original volume. Okay. So 2 times the osmolarity for this number, which means that after a while, we're going to end up with 2 times the cell volume. In this example in B, we have the opposite situation. So we're in a hypertonic solution. So we have lots more solute here, lots more impermeant solute outside our cell. And we can see that the osmolarity inside the cell is only half the osmolarity outside the cell. Then after a period of time, we have water moving out of the cell so that we equalize those concentrations, equalize that osmolarity. And when we finally come to equilibrium, we now have a cell volume that's half what the original was. So you can look at essentially how many times the inside the cell is versus the outside the cell for that osmolarity. So predictable amounts of size change. The next piece we're going to talk about is transport across epithelia. But more big picture here, what we want to get to is thinking about the fact that our cells are not all tiny little circles. They have sides, the sides are touching different things, and we're going to need to be able to move stuff, big picture, across entire cell layers. So here we're talking about epithelium specifically, but as we move into our unit on the brain and neurons, we're also going to be thinking about moving things across a neuron, so across one of our nerve cells. Okay. So we're starting to dive in on this idea that cells have different shapes and that kind of matters. So when we have transport going across the cell, we're going to want to be able to name the different sides of our cell. So for epithelial cells, so epithelium is where you have the lining of some body cavity or like the outside of the body. So here specifically what we're looking at is the lining of your intestines. So the inside of the intestines is that yellow part, and the blood flow all around the tube is the blood at the bottom here. So you can see that we have a membrane touching our gut tube, touching the contents of the intestines up at top. That's our apical membrane. We have a side down here touching the blood, or near the blood anyway. This is our basolateral membrane. We have a structural layer that isn't its own cell, but we have this basement membrane that they're all kind of sitting on together. You can see that epithelia are characterized by being stuck to each other with tight junctions. So there's no there's no leakage really, or very minimal amounts of leakage under normal conditions here, less than in other tissue types. Okay. So that's orienting us to these cells. Okay. We have our apical membrane, we have our basolateral membrane, we have our tight junctions on the side. Okay. So we can use the epithelia as a way to look at our different types of transport working together. And those of you who took bio of the cell, this example may be familiar, I think. You saw it in a different form in a problem set once, but we're going to walk through it. Okay. So what happens when we're trying to move stuff across membranes? Often what we do is set up a gradient using a pump, usually a sodium-potassium pump, because sodium is just super important in cell function throughout the body. So what we can see here happening is that action of the sodium-potassium pump on the basolateral membrane. So it's acting down here at the bottom. You can see that sodium-potassium pump. Okay. So the sodium-potassium pump, its job is to move sodium against its electrochemical driving force. So it pumps sodium out of the cell and it pulls potassium into the cell here. Okay. That process takes ATP, requires energy. So it's an example of primary active transport. So that's how we set up this situation. Okay. We can also see on this figure, we'll focus on the figure first. So we can also see on this figure in green, so that indicates on our figures usually that we have passive transport. So we can see here that we have a little bit of potassium like leaking out of the cell through a channel. You can see a little bit of the same thing going on here, at least in this image, for sodium on the lumen side. So if we have open channels, these are the directions they would move, because sodium would be moving towards this artificially low concentration of sodium inside the cell that we've created with that pump. And the potassium is escaping that high concentration of potassium that we're building up outside or inside the cell as we build this up. But the bigger picture that we're interested in here in this case, when we're thinking about intestines, but more broadly, the point of using sodium as a gradient is that we like to move things that are precious to us like glucose, right? So if you eat a donut, you want to pull in a bunch of glucose to your body and to your bloodstream so that you can take it to cells that need energy so that they can do respiration, do metabolism, and break it down for energy. So we can see that the way we do that is that our sodium in actuality isn't just going through a channel on its own. What it's doing is linking up with the transport of glucose. So we can see here, sodium moves down its gradient the direction it wants to into the cell, and it's pulling glucose with it. So this is a co-transporter for that glucose molecule here. So this is an example of secondary active transport. Okay. Then on the other side, we've packed all this glucose into the cell using this secondary active transport, using this sodium gradient. That means that glucose now has a force, a chemical driving force, to leave the cell through passive transport because we use that secondary active transport to concentrate it inside the cell. Right. So that more formally, that low intracellular sodium, so that's low concentration of sodium inside the cell, got caused by outwardly pumping that sodium across the basolateral membrane, creates an inward gradient, so it creates a pull for sodium to come into the cell. We have a little bit of leakage across the apical membrane. We're transporting it there, but really mostly what we're doing, or the reason we would be looking at this primarily, is to look at that secondary active transport of glucose here. Okay. We then see facilitated diffusion on the other side through the basolateral membrane. This glucose is too big to squeeze directly between phospholipids, so it has to use a transporter, so we can see that. Right. Linking that up to the osmosis piece. All right, so we're not going to focus too much on what's going on with the water and the epithelia. So what I just want you to know from this piece is that as we're moving those solutes, they are pulling on the water. Okay, so the water flow in general is just going to go towards wherever we have large solute concentrations. Okay, so what I'm saying is you can mostly skip this so long as you understand the basics of what's going on with the osmosis. Okay. But in this example, this would just be touching into that concept. So cystic fibrosis is a disease that causes, among other things, a really thick lining of mucus in your lungs. Okay. And so one thing that happens here is that this messes with water transport. So normally you have chloride ions leaving into the airways, okay, through active transport. Sodium ions are attracted to them because of charges, so they go join them. So that builds up a bunch of ions here, which exerts a pull on water. But one of the things that happens in cystic fibrosis is the system breaks down because of that thicker mucus. Those chloride ions have nowhere to go because they get kind of stuck. So there's no negative charge of chloride ions pulling on the positive sodium, so it doesn't move either, which means that water overall doesn't get transported across the cell. Right. This is the piece that we do want to understand for neurons. So I'm going to pause and zoom in a little deeper here. Okay. So when we are thinking about moving large collections of molecules, we're not necessarily always going to be moving them through a transporter, through a channel, something like that. So specifically, when we start to talk about neurons communicating with each other using neurotransmitters, a bunch of those are going to be just in general, too big to just go through their own little gap in a membrane somewhere. Okay, so this is where transcytosis and specifically our processes of endocytosis and exocytosis will come into play. So if you have something that's too big, so say you have a collection of molecules that you're trying to get from the lumen, or a collection of molecules that a cell has made, we'll often want to move that whole collection in its own separate little membrane-bound baggie. Okay. So what we can see happening in this image is, say you want to take something in that's large over here on the lumen side. Okay, so we have this large particle. We're going to be non-specific about what type of molecule it is. Okay, so if you want to bring this big thing into the cell, it's big enough, you're not going to have a transporter for it, because a transporter is a protein. There's only so much space you can make in one. Okay, so what can happen is you can have that particle, or whatever it is, come in and bump into the membrane of your cell. Okay, it's bumping into the membrane here. You can see how it's pushing down here. And what we're actually doing is forming a little pocket of membrane and then allowing that pocket to break. Okay, so what we've done is we've formed a vesicle. So vesicle is a word for a membrane-bound sac. Right, so we've done that by pinching off a little bit of that apical membrane We pinched it off and used it to surround that particle. So that's the process of endocytosis. Endo means taking into, cytosis for cell, okay? So we took something into the cell by allowing it to press in, we call that initial process invagination, but like it pressed in, made that dent, broke off as a vesicle. Now it's in the cell. We can have the same thing happen in the opposite direction. So we can take it and then move it across the cell, right? Or you can imagine if this is like a nerve cell, maybe you made something and put it in a vesicle in the first place. And so once you have something in a little vesicle in the cell, in this little baggie, you can then take that bubble, move it up to the membrane on this other side. And because that membrane is just made up of a bunch of phospholipids, right? When they bump into each other, you can think of like soap bubbles touching each other and merging. Right? That's what's happening here. On this other end, we have that bubble merging into our cell membrane on the other side. As it does that, that bubble breaks open, that vesicle is breaking open, releasing that particle on that side of the cell. So that's the process of exocytosis. So exocytosis outside is the exo part, the cytosis is the cell part. So that's how you get something out of the cell, is exocytosis. So we'll see that exocytosis part specifically as we talk about neurotransmitter release in our unit on nerves in the brain. So that is the main piece that you want to make sure that you understand. So on Monday, we will begin talking about neurons, and I'll send you out an activity to